So it's a few minutes early, but I get to start early, which is good. So I get to choose. That's also good. So thank you for coming along. I really want to leave that message. I really appreciate everyone who's taken the time to come along to the session. That's my key takeaway, that I really appreciate it. So before we start, some giveaways and some prizes, because that's why we're all here at the end of the day, right? So question number one, I've got 3 prizes here. They're not bad, actually. They're nice kind of 3-way adapters with a USB and a little setting, as long as you're in the US or the UK or Australia, but I don't think New Zealand is part of Australia. I'm not kind of 100% sure about that. You get to use this, right? So I've got 3 questions. So the first question to the first lucky person is, TechEd wasn't actually the first conference. We've talked a lot, Microsoft have talked a lot about how this is our 20th conference. That's not quite correct. I haven't been to all of them, but I certainly went to the first one. And the first one wasn't called TechEd. It was the year before TechEd started, and it had a different name, and it was also in Auckland. What was it called? Hand up, please. Must be one person in the room that knows that. There's no one over the age of about 100 here. Yes, gentleman with the glasses. Pardon? No, not Texas. Very close. Dev Days. Good man. All right, second of 3 questions. So you don't have to listen to any talks or see any slides. You just get gifts. How good can this be? What was the code name for in-memory OLTP in the old version of SQL Server, SQL 14? Hence, Hackathon. And the last one, which is the one I particularly want to give away, please put your hand up. It's a technical question, so don't get too scared. What is the default transaction isolation level of SQL Server? I can't give you 2. Recommitted. Watch your heads. All right, excellent. Now you can leave, you 3 guys. See, that's awesome. All right, so what are we talking about? We're talking about in-memory OLTP, the code name for which was Hackathon. My name is Pat. I've been with Microsoft since 2002, doing different things, but mostly SQL Server, especially the last kind of 5 or 6 years. I've kind of met a lot of people in the room over that time, which is, maybe I've been doing this for too long. So we introduced Hackathon in-memory OLTP. We introduced it. I'm going to talk about what it is, but just very quickly, one quick question, please. Hands up if you're using SQL 14 in production. So about a third of you. Hands up if you're using in-memory OLTP in production. I see no hands. Okay, that's a little concerning. All right, so let's kind of explore that, maybe talk a little bit about why that might be the case, and some of the things that we, Microsoft, have done in SQL 16 to try and encourage you to change your mind and think about using it. So the presentation was actually fundamentals, what is Hackathon, what is in-memory OLTP, and then talking about what we've done in 14 and how it's changed in 16. So the focus is on how it's changed in 16. But that isn't going to work for you guys because none of you have used it. So you need to know more about what it is and also what we've done in 14. So I'm having to kind of change the presentation briefly based on that last question, which is fine. I like that kind of challenge. But we'll also are going to talk about the new things in SQL 16. And there'll be plenty of time after the session or for the rest of the week, come chat to myself or David about this technology. So I'm going to talk about 3 things. This is the focus of the presentation. It's also what I want to leave you with, which is, what do we do? What is it all about? What does it mean to say in-memory OLTP? What did we do in SQL 14 to make that feature possible? And what are we doing in 16 to make it more usable? All right, so that's the focus. And I'll take questions at the end of the session because I need to go relatively quickly. So I hope you've had coffee. All right, so a little bit about the basics. Hardware trends with CPUs and what kind of drove in-memory OLTP. So Moore's law, things kind of doubling in capability in very short time periods. And you see here from the slides, in terms of the numbers of transistors, which is our green line, that CPUs have, that's kind of grown exponentially. And we're getting processors now with sockets with lots of cores. That's getting bigger. But what's not happening, if you look at the other lines, is the CPU clock rate kind of stalled. It's kind of around 2.53. It hasn't really gone up much. And overheating is still a classical challenge too. If you look at the lower blue line, you know, things melt and things kind of reach a capacity in terms of CPU cycles. So the way forward has really been about more CPUs rather than faster ones. So doing things in parallel, and parallel computing has become a real focus of the computer age, not only on site and on premises, but also in the cloud. So massively parallel scale. This is kind of a key part. And memory prices coming down over time. They've always been kind of historically one of the more expensive pieces, but they have come down over time quite considerably. So Microsoft, having seen this parallel trend in CPU usage and in the fact that memory is coming down in price, we looked at ways to maximize that kind of forward thinking in terms of how SQL Server is architected. So I want to spend a little bit of time on this slide, mainly because nobody's using this. So if I kind of take 5 seconds and move on to 16, you're going to leave the room thinking, what was all that about? So I need to take you through it a little bit. So the way that SQL Server normally works, you guys know this, but just to repeat it, you've got data in your data files. It gets read from the disk. It gets read into pages. They're 8K pages. The rows are on the pages. And they're read into a thing called a buffer pool. And then as you're giving data back to clients, data's read out of that buffer pool. Changes that are made from the buffer pool, they get written back to disk. That's a lot of work. That's a lot of architecture. That's a lot of coding to take care of disk latency so that you can use an in-memory cache, right? The whole product is architected really to make that work well and to keep this buffer cache fresh. That's how the product is built. So we don't do that in in-memory OLTP. We're not using the buffer pool. And we're keeping data in memory. And we're keeping data in a different part of memory. And the memory is direct pointers to rows. So the rows are kept in memory. They're direct pointers. It's very, very fast. And the indexes are in memory as well. So you just got to kind of consider that. Everything's in memory. Everything's a lot quicker. And this buffer pool is not being used. We've got here no write-ahead logging. That's not strictly true. There are some cases where that still happens. So in what I'll refer to as standard SQL Server, if you like, disk-based tables, as SQL Server is working and it's doing work, things are being written to the transaction log. And then that transaction either gets committed and a commit mark gets made in the log, or it doesn't get committed. And parallel to this, lots of changes are being made to data pages as a separate process. So you've got things going on in the log, you've got things going on in the data files. If SQL Server breaks and has to run crash recovery, it's now got to do two things. It's got to look inside the log to see for any transactions that haven't been committed yet, right? But they may have had the data pages updated. So it's got to undo those changes because they never got committed. Or there may be changes in the log that were committed for which there are no corresponding changes in the data pages, and it's got to roll those forward. Those are two processes that have to happen on crash recovery, and there's a lot of work in the log, and the log becomes a latency, it becomes a bottleneck for SQL Server. This doesn't happen in in-memory OLTP. The only time the log gets written is on commit. It's the only time the log gets written. So that means two things. There's a lot less traffic to the log, right? There's a lot less traffic, and there's no need to do an undo phase because you won't have things written to data files that haven't been committed, right? So it's a real bonus in terms of how that works. Now let's talk about T-SQL native code compilation. The other thing that happens within memory OLTP is we compile on the fly C code, which I can show you quickly, to support any tables or what we call native stored procedures that you create. So you create an in-memory table, you load data into it, there's the C code behind the scenes. It gets coded into a DLL at runtime and loaded into the SQL Server address space. That's a big change conceptually to how SQL Server is working. Similarly, for your stored procedures, you compile a stored procedure at runtime, a DLL is get built and loaded into SQL Server. It's very, very fast. And I'm quite comfortable to say it's lightning fast. So this stuff runs hot. But we'll see as we go through that there are reasons why you might just not always use it, because you might be thinking, if it's really fast, Pat, then why don't we just use that all the time? There are scenarios where that doesn't work too well. So you need to understand the use case for in-memory OLTP. All right, but it's fast, it's useful. Conflicts are rare, so full ACID support. For those of you born in the 50s, that's not a noun. It's an acronym, right? You should understand what it means. But what it's actually allowing you to do is manage concurrency in SQL Server. So the standard behavior of SQL Server is to take locks. So a gentleman said that the default transaction isolation level is recommitted. What that means is when you read a record in SQL Server, you take a shared lock. That's what SQL does on the page or on the row. If someone else wants to update that row, that needs another lock. Right, needs an update lock and then an exclusive lock to update the row, which is incompatible with a shared lock. All right, so readers and writers block each other in SQL Server, which is the opposite of how Oracle works. So you get blocking, but you don't get blocking in in-memory OLTP because it doesn't take these shared locks. And it doesn't take latches as it's reading pages in and out of the buffer pool. So no locks, no latches. Right, it's going to work really, really quickly. It's an optimistic concurrency control. Just like Oracle, if you had 2 concurrent updates, the last one in will fail. And we'll get an error message to say this row's changed while you've been looking at it. But there are no locks while you're reading and writing. This is a big difference to how SQL works. So very rare conflicts, integrated tooling, the in-memory capability, the in-memory technology is built into Management Studio in terms of the tooling and the support. You don't have to install different components or, dare I say it, Oracle cartridges or anything like that. It's just part of the product. So it really is a key change, quite an enabling change for SQL Server. So just quickly, let this build. Here's our standard SQL query execution. We've got our tables, data's read into the buffer pool, the data's stored out on disk in a file group, and concurrently we've got lots of changes being made to the log. This is 101 SQL, this is standard stuff, this is how SQL Server works. But now we've also got these memory optimized tables, and we might take some of our disk-based tables and move them into this memory optimized technology. So now they've moved across here. They've got their own file group. So when you create one of these databases to support memory optimized tables, that's a separate file group, and you have to say this file group is going to contain these memory optimized structures. So that's something you have to do from a SQL perspective. There is an interop mechanism to allow your disk-based tables to interact with your in-memory tables. You need that because you might have transactions that need to access both types of tables. That's called query interop. All right? That's not the native code. So if I compile native code, if I compile a native piece of C code behind the scenes by creating a native stored procedure, that gets compiled and it can only access these native in-memory tables that I've created. So you've got 2 ways to manage this. I have a native stored procedure that only accesses in-memory tables, or I have the old style, should we say, T-SQL running interop, which can access disk-based tables and memory-based tables using interop. So there's 2 approaches to manage that problem. So this is kind of a high-level picture of how this architecture looks. So I just need to mention that briefly. There's also this concept of non-durable tables. So I can create an in-memory table that doesn't survive a restart. Anybody know why I might want to do that? And there's another USB 3 multi-port, not a bad little present here. Why might I want to create a table that is gone when my SQL restarts? Hands up, guys. Caching, an example?
So if you've got a website.
Yeah, that's good. So I might want to do some kind of web caching. I've got a website, my website comes back up, my SQL comes back up, I've got new sessions, so that I didn't need to keep what I had before. So those tables are going to be lightning fast. So if you've got a developer and application scenario where you need a cache, this is awesome because it's not even going to write to the log. It's just going to keep it in memory. It's just not going to hang around and survive a restart. All right, so that was kind of a lightning picture of the technology for those of you that haven't seen it, which is pretty much all of you. So first steps, what did we do in SQL Server 14 to make this happen? So Hackathon was a code name. It's a SQL 14 technology. You could probably guess, although I won't give away kind of my remaining swag, you could probably guess what release or edition of SQL Server this technology relates to in terms of the SKU, and you'd be right. The value proposition for in-memory, so very fast. It talks here about 30 times faster. We've seen different, you'll see lots of statistics, you'll see lots of white papers, and it depends who you talk to. But it really is very, very quick because everything's in memory and there's very little disk traffic. Your bottleneck really becomes your transaction log rather than your data files. And that's a huge shift in where your performance curve is going to sit. All right? So it's a very fast technology. Part of SQL Server Enterprise Edition, you can take a gradual approach to implementing in-memory technology. So you don't have to take all your tables and turn them into in-memory components. You wouldn't be able to do that. There's work you have to do. This technology is really aimed at some key scenarios. You want to run very, very high throughput, OLTP throughput. You've got some blocking because of the way that SQL works. It takes latches. If you look at your SQL Server, you'll never see a CPU running at more than about 80%, unless you've got a bug and your app doesn't work, and then it might stick higher. But SQL itself won't drive it more than about 78, 80%, because it starts to take latches the higher you drive it. And we've got lots of examples of that. So this is kind of the constraining factor in terms of CPU throughput for a SQL Server machine. So you're not going to see that. It's going to be very, very fast. It's integrated with always on. So for those of you that are aware of this always on technology in terms of high availability and disaster recovery, I won't go into detail, but it's real-time communication between a primary and a secondary of transactions, and then your secondary can be brought up on failover. Always on is aware of this in-memory technology, so that takes care of those as well. So those are the target scenarios, high throughput OLTP. So there were some constraints. There are some constraints. There are some things that you can't do in SQL 14. But they are fully logged. As I said, every commit, so transactions are being bulked together in one insert essentially into the transaction log. You still have to write to the log for recovery. So these transactions are durable. Talking here about non-durable tables as better temp tables. For people that use table variables in their SQL code, table variables still use tempdb, right? They're not this magic in-memory stuff that doesn't use tempdb. Table variables are backed by tempdb, right? Believe it or not, they are. And that brings with it some potential bottlenecks. Not these things, they're not. This is in-memory. So this is a better table variable, right? So that's kind of from a developer perspective. These native compiled stored procs, they're very, very fast. I'm really comfortable talking about the speed of this technology because it really is quick. Interop, I've talked about near full T-SQL surface area. There were some constraints. There are some constraints, particularly in native code around the type of SQL that you can and can't do, and I'll go into that in a little bit of detail shortly. This is what I was talking about before, using table variables and replacing them with in-memory table types. All right, so this is the only slide that talks about how fast this goes. It's really, it's just to bring home how quick this is. David Lyth in the previous session on Upgrade, he talked a little bit about this BWin customer. We've got a lot of customers, there's a lot of case studies. You know, you can go and read about this yourselves, about this technology. But these are online gaming people, and their business is based on how many bets they take in very small periods of time. And there's numbers here about some of the gains that have been seen using this technology. So you really care about this if you've got real requirements for throughput, real high-speed stuff. A lot of you don't have that, but some of you will. Some of you need to push things through really, really quickly, and this is where you need to go if you need to do that. Or if you're experiencing any blocking because of the way that SQL works. This is an enabler for that. All right, so I'm not going to mention the numbers. I just leave it there for you to look at. But it's very common. We have lots of similar case studies relating to the speed of this technology. So where does the performance improvement come from? Well, the main one is the no locking and no latching. So SQL Server performance tuning is all about something called wait types. I don't know how many of you are familiar with these, but SQL's always waiting for something. And the way you profile or measure your box or you do performance tuning is you collect all this wait type information over time and then you measure it. So if your SQL is spending most of its time waiting to write to the log, well, now I better go fix my log latency. Or if it's waiting for page latching, maybe I haven't laid my data files out across the disk properly. Or if it's waiting on page 2 of TempDB, maybe I don't have enough TempDB files. You learn about your environment based on the types of waits that SQL is experiencing. But it's not going to experience any locks or latch waits because there aren't any. So there's very few I/O waits. The only I/O is to the log file, and that's only on commits. You kind of see the point? There's a lot less waiting because it just gets the CPU and does its thing. Right? So that's quite a big deal. Natively compiled stored proxies are just faster. There's quite a good research paper written on this technology. It's quite long. I've read it a number of times. I think by about the 5th time I understood about half of it. It's not the easiest thing in the world to read, but it talks about the implementation of this native codes. And it's all based on go-tos. And you'll be thinking, oh my God, you can't use go-tos. But that's how it's written, how it's developed. And there are reasons for that. It's all in line. There are no external function calls. It's very, very fast in terms of these native stored procedures. Reduced bandwidth because we don't write to the log. And we don't write to the data. Oh, sorry, we do write to the log on commits, but that's the only time we're packaging up writes. And the only time we go out to a file group is something called the checkpoint process, which is a background thread or a set of threads which are spinning log output to checkpoint files, just like the checkpoint process in standard SQL Server. Everything's sequential to memory optimized file groups. There's no random I/O, so everything's sequential. So all of these things taken together, they count for a very noticeable performance improvement. What hasn't changed is anything around the client. All right, so the tabular data stream, the client protocol, packaging up data and sending it back to the user, none of that stuff has changed. That's all the same, right? But everything down the stack here is really quite different. Okay, so this is where these performance gains are coming from. All right, this is the only slide I've put in about what it looks like really internally. Had I known that nobody was using it, I may have put a few more in. But a row in memory looks a little bit like this. It has a header and it has a payload. The key point you really kind of care about on the header, just quickly, is the begin and the end timestamp. The begin and the end timestamp of a row, they determine the lifetime and the scope and the visibility of that row in relation to transactions that are running concurrently with the data. So if I run a transaction and it sits between the begin and the end timestamp, my start time of my transaction, this is the row that's visible to me. If that row gets updated, updates are managed by changing the end timestamp with the date of the update, and a new row gets created with the date of the update with infinity as the end time. So now I've got two rows for the update, the row that it used to look like and the new row, with the key date being the time the update was made. And then as time goes by and transactions age, that older data is no longer needed because the oldest transaction will post-date the end timestamp of the data. And then the garbage collector can come in and remove this data from memory. So it's a very key concept, this idea of the begin and the end timestamp of a row in memory, because that determines who can see it in terms of the transactions. Then you have pointers to indexes. There are two types of indexes. We'll talk about them a little bit, but not in any depth. There's a thing called a hash index, which is for lookups, and there are non-clustered BW tree indexes. We're a little bit different to B trees, which are range index, which is a non-clustered index. You can have a maximum of 8 indexes on a table. They can be any combination of these lookup and range type indexes. But 8 is the maximum because it takes space in this payload, in this record header. All right, so that's kind of a very quick introduction to Hackathon or in-memory OLTP in SQL 14. It's very quick. It's amazingly quick, actually. All right, but there are a number of constraints and a number of limits and things that you can't do in SQL 14 with Hackathon. Unfortunately, most but not all of these have gone away with SQL 16. But it will make your life a little bit harder if you want to implement this technology in a SQL 14 environment. So the first one, which personally I don't think is a great limitation. We've set a maximum of 256 gig as the size of an in-memory table. I haven't seen too many of those in New Zealand. I don't often see 256 gig databases, to be honest, but there are some. But even those tend not to have a single table of that size. So unless you're sitting there thinking, well, my 500 gig table isn't going to work too well, but I kind of doubt that. Regardless, that limit's gone away, and it's been increased to 2 terabyte. There's a bit of information there about why that limit actually exists. But again, it's not really where I want to spend time. But that's the limit for a size of an in-memory table in SQL 14. It's 256 gigabytes. SQL 16, 2 terabytes. It's a pretty large single table. That's our limit. But Windows Server 16, we're talking about 12 terabyte machines, right? Windows Server 16 supports 12 terabyte hardware. That's a lot of memory on a machine, right? Do you want to scale up to 12 terabyte? Maybe you'll start thinking about scaling out before you scale up to 12 terabyte. But if you did, you could load your tables in 2 terabyte chunks. So some of the challenges in SQL 14, this one's talking about these data files. So as in-memory OLTP is running, as transactions are changing, things are getting written to the log once they commit, and there's a background process, which is a checkpoint process. It's not the same checkpoint process we know and love. It's slightly different, but it's doing much the same work. It's harvesting the transaction log, and it's writing what's called data files and delta files. And the data files contain all the data that you've inserted, and the delta files contain all the rows, just the keys of the rows that you've deleted. So you've got all my data that's been inserted in my data files, and all my rows that have been deleted in my delta files. And then when SQL Server has to recover, as it's going through the data files, it's also going through the deltas and skipping any deleted rows. Right? This is how it's working. So these data and delta files are continually being created over time. And they can get full of deleted rows. This is what these red bars represent, are the deleted rows. So you get to a point where your storage isn't too optimal, because you've got these large files with deleted rows in. So this process will come along periodically and merge those deleted sets into one set. So you can see from the numbers here that within the range 200 to 400 in the grey bars, these are merged together. These can be removed. So you've got one fewer bar once this merging has actually taken place. This is a background process that's running. And it was pretty slow, or slower, it's all relative in SQL 14, because it's using internally something called FileStream. It's still using FileStream in SQL 16, but not to do this. So this challenge has gone away. All right, so that's one key improvement. TDE, if I want to encrypt in-memory tables in SQL 14, there's no support for that. I can't do that. So in SQL 16, I can do it, have to drop my keys and recreate my structures and put my key pairs back, put my certificates back. But we support TDE in SQL 16, right? What else? Scaling. So this is a picture of this checkpoint thread, which is going through this transaction log here, and the log is containing both types of tables. We're seeing on-disk tables and in-memory tables in the log, because there's only one log. We haven't added log files to support this. And this checkpoint process has to go and it has to harvest these entries from the log file and write them out to disk. And that's a single-threaded operation in SQL 14. And in SQL 16, there's one thread per container. So what's a container? When you create an in-memory database, as I said, you have to annotate or you have to specify that the file group you're adding to the database contains in-memory data. When I add a file to that file group, that's referred to as a container. There's one thread that's doing this checkpoint processing per container. And when I do recovery, when SQL Server does recovery, when it's restarting, these containers are processed in parallel in order to read the data off the disk and put your in-memory tables back. So the more containers you have, the better use of parallelism you'll be making to reload these in-memory structures. So it's bound by the speed of serial I/O that you're supporting. So the more containers you have, the more concurrent use of that serial I/O in terms of recovery. So that's what's going on. That's what's going on here. I'm going to skip through this one. All right, so in terms of challenges to somebody that wants to do this, because I'm really selling it quite strongly here because I think it's a good technology. But the problem is it's not an easy thing to implement in SQL 14 because there's a lot of constraints around it in SQL 14. You can't change the schema once you've created an in-memory table in SQL 14. I can't add an index once I've loaded a table in SQL 14. I can't use certain types of SQL in native compilation in SQL 14, like an outer join or a union. I don't have foreign key constraints in SQL 14. These are quite serious limitations for some types of applications. They don't stop you doing it, but they certainly make life harder, because a lot of this stuff you're going to have to support yourself. So it's kind of what's in the box versus what do we have to create. So being able to change the schema is really important. So in SQL 16, we've added the facility to run an alter statement. You can alter the stored proc to have it recompile. There are no auto update of statistics for in-memory tables. So in SQL Server, I can turn on auto update of statistics as data's changing, round about give or plus 20% change. Auto update stats will kick in and rebuild my statistics, either synchronously or asynchronously, depending on how I've configured SQL. That doesn't work for in-memory tables. So the DBA, has to update the statistics once you've loaded the data. So you may not always have the best query plan or the best plans for your stored procs, and you can't easily change them in 14. You have to drop and recreate them. All right, 16 is going to let you do that. It lets you run alter procedure. It lets you run alter table, add and remove columns, add and remove indexes. You need this. That's a really useful thing. Especially something called the bucket count. Right, the bucket count is really important. Change hash, index, bucket count through index rebuild. The hash index is for key lookups. So it's building a hash table. It's going to the hash table with your key, running it through a hash function, and going to the appropriate part of the hash table to find your row based on the hash of that key. Each entry in that hash table is called a bucket. So in SQL 14, you kind of need to know how many rows you're going to have in this table, how many distinct rows you're going to have in the table, because you need to know how large that bucket is going to need to be, because that's your memory constraint in terms of your memory requirements for those structures. And there's no way in SQL 14 to change that bucket size without recreating the table. So you need to do a bit of homework to know your kind of how many rows you're going to expect, distinct rows, which is a little bit of a challenge. In SQL 16, you can run an alter statement and rebuild the index with a new bucket size. So now I can learn, based on my workload and my observations, what that bucket size needs to look like. And that's a very important concept for the hash index in an in-memory table. So this is just examples of the things I've been talking about. We don't need to spend too much time, but the ability to rebuild the index is not there in 14, it is there in 16. These types of T-SQL, not supported in 14, but supported in 16. All right, so some quite significant changes between 14 and 16 in terms of in-memory OLTP. More of the same here, running an alter table. Okay, so I think we've kind of done that to death, really. But you need some of these features. Changing the stored proc, altering a natively compiled proc, just recompiling it, and I'm good to go. Because I need a new plan, my stats have changed, I've reloaded my data, and I need to keep going. So I can run SP recompile and get a new plan. All right? All the stuff you're used to on your daily basis that you want to be able to do. So just a quick list. I don't expect you to read. I want quick question.
2014, can you delete the tables if you're recreating new tables?
Yeah, you have to drop them and recreate them. So if you had to reload them, for example, I'd have to put that data somewhere. I'd kind of have to do a select insert and bring it back. Yeah. It's just more work. You know, you really want to be able to do this. So you can do all of these things, but it takes longer to do it, more operations. The one I've called out in red, just quickly, I decided to paint it in red. In SQL Server 16, column store structures are supported as in-memory OLTP structures. David referred to it very briefly in his session. If you're using column store indexes, these can be in-memory OLTP structures in SQL 16. What that means for you is that, at least in theory, you can do analytics on an OLTP system. You still need to be really careful when you do that, because most problems that people get into is due to mixing reporting and OLTP workloads on the same server. That's where everybody falls into a big black hole. So you still need to be really careful when you do it, but this is very helpful, the fact that you can have a column store index as an in-memory table. Because now I can do high-speed analytics, things like fraud detection, real time, rather than having a separate ETL process which I have to crank through, because that takes time to do that. Right? I'm not saying just go do it. You have to be very careful mixing these two workloads, but it's something you can go and think about and at least do some experimentation with. Yeah. All right, scaling. I've talked a little bit about that. Multiple threads to write to the log. Those multi-threads are also used for recovery. Merging is better to merge these checkpoint and data files together. There are lots of views to look at these structures. So there's really quite a big change between SQL 14 and SQL 16. TDE I've already mentioned, support for TDE in memory structures. How do I get from A to B? If I want to use all this great stuff, how do I actually do it? So I'll show you a little bit of the reports. I'll show you some of the reports that you can run to help you do that. This transaction performance analysis overview report. You used to need something called MDW to do this in SQL 14. You had to install this management data warehouse in order to be able to get at this report. That's no longer the case. It's now built in when you have these structures, which is much better. Not a lot of people are using MDW, and it was an extra thing that you had to kind of install and configure. So it's nice not to have that. So let me just switch over and have a quick look. Just still in the interests of time here. Hopefully, all right. So I've got a virtual machine. My virtual machine is SQL 16. So what I've got here is alter support. So I'm going to create a database called Ignite OLTP. It's going to go off and drop this database and recreate it. I'm just going to have a quick look at my database ID, just because I'm going to point something out. It's 15. So I've got an in-memory database. So here's the syntax. Right, if I'm going to start doing this stuff, I have to say that my file group contains memory-optimized data. Right, I have to tell SQL Server that I'm going to do that. And then I have to add a container, which is a file. So this is referred to as a container, but it's just a file that's being added to my file group. So now I've got the potential to store in-memory database type data, in-memory table data in this database. So here's what the syntax looks like if I want to go and do it. I'm creating a table. Here's a table sales orders. It's an in-memory table. I say with memory optimized equals to on. Durability is schema and data, as opposed to the schema-only ones that we talked about before. So this is going to persist, right? I'm going to be able to recover this table, all right? And I'm using a non-clustered hash index, which is my key lookup index in this particular case, right? So this is the syntax that you'd want to write, or that you need to write, to create one of these structures. And similarly for stored procs. So here's a stored proc, insert orders. Some extra syntax. I'm going to say it's natively compiled. It's schema bound, which is how these things have to be, and execute as owner. So you can't change schemas, you can't execute as somebody else. And the reason for all of that is performance. Everything's done statically at compile time. So you don't want the context of who's running this piece of code to change at runtime, because then that would mean a call out from this native CDLL. All right, so you can't have that. So you declare everything statically up front. This is a performance optimization. This is why you see this kind of stuff here. Same with atomic. This is an atomic transaction. Everything has to fail or not fail within a single transaction, because you can't have blocking. You can't have this thing going out and waits. All right, it's all done in a single transaction. So this is some code to create one of these stored procs. So let's go and do that. So here's my stored procedure for my native code. And then we've got code here. And what I want to show you just quickly, it's a little bit different to what I was going to talk about, but I think you guys are in a little bit of a different place. What you see here is the database ID of the in-memory database that was created. You see the table ID of the table that was created, and you also see the ID of the stored proc that was created. If you go out on disk, right, if I go out on disk to those in-memory OLTP structures, if I take that folder location, let's go and insert some orders first, actually. I'm going to insert 100,000 rows into that in-memory table. So let's go and do that. So 3 seconds for 100,000 rows is not too shabby. All right, and then I can go and look at the index, and it tells me I've got a very long chain length. This means duplications, because my bucket count was very, very small. When I created a table, I said use a bucket count of 20. Right? So I've got lots of keys that are different that are hashing to the same bucket. So SQL has to wander down each of these buckets to find the key that I'm looking for. So having a bucket count that's too small, it's great because I don't use much memory, but it's not very good for performance because SQL has to go wandering through these chains. So you don't want these average chain lengths to be more than kind of half a dozen or so. But now I can rebuild, right? So I can rebuild the index. Which is kind of handy. All right. So those are the kind of things that we do. Then I can go and I can say, well, show me that table. Show me that table and show me this average. So what I'll do actually is put on the execution plan. And what we see is an execution plan for an in-memory select. And it runs parallel now. Before, I didn't show it to you, but with a bucket count of 20, it wasn't able to take advantage of parallel streams, so you would have seen a very different plan. So very, very fast structures, the ability to run alters on the fly. In terms of T-SQL coverage, just quickly speeding up a little bit, I'm not going to run through all of this. Coverage here, you can do outer joins, you can do a case, you can do a union. All of these things you can't do in SQL 14. Right, so these operations, these T-SQL operations, they're available in SQL 16. Behind the scenes, what you're going to see, if we go and look, just quickly, if we look at folder structures, you actually see very different. You see all of the rows that have been created. So as a DBA, you need to take care of this, right? If I go to this folder, this is where everything's been set and where these structures are kept. So although you don't have MDF files, you still have to take care of those structures. So if you remember, my DB ID was 15. So this is my in-memory database. And this is the code that was created when I created that in-memory table and that in-memory stored proc. So it's behind the scenes, right? And this is the object ID. That was the object ID. And you've got T for table and P for stored proc. So here's my table. And I can go in and I'm looking in Visual Studio at the C code. Because that C code has been generated specifically to support that table. Different table, different C code. Compiled at runtime, DLL loaded into the SQL Server address space. This has never been done in SQL before, right? We're not in Kansas anymore. So it's quite different. So let me just switch back here. All right, so again, in terms of speed, we can now run parallel for reporting in-memory OLTP. You have this issue of being able to use the full T-SQL coverage. You have full T-SQL coverage in SQL Server 16. It's pretty full coverage. You've got unions, you've got outer joins, subqueries, all the things that you'd expect have been added to native code support in SQL 16. All right, let's talk a little bit more. Foreign key constraints. Absolutely required, right? I mean, you can't have relational databases, or you shouldn't, without foreign key constraints. Triggers is an appalling way to manage this problem. You really want foreign key constraints. So not having them is actually quite a significant limitation, I think. So these are here in SQL 16, amongst some other types of things that you can do. Nested stored procedures. If I can't nest stored procedures, I can't have stored procs that call other stored procs, which means I can't factorize my code, which means I get a lot of code duplication. That's not great either, right? So some of these limitations are a little painful. That doesn't mean that you shouldn't take your SQL Server 14 if you've got it. Hopefully you're not sitting out there running on SQL Server 2000, and use this technology, right? It's great, but you'll need to do some extra work to make this work in a SQL 14 environment. There is a good Books Online reference that talks about all of these constraints and how to work around them if you're doing this in SQL 14. Things like triggers, they're not there in 14, but they are there in 16. Entity framework support through Mars is multiple active results set. If you're doing entity framework link type stuff that tend to open multiple connections, you need SQL 16 for that. So migration. Let's talk a little bit about migration. It's a good product, but how do we get there? How do we get to in-memory? So what you're going to do is you're going to run workloads. You're going to test bed your production environment, and as you're running, information's being kept in DMVs by SQL Server. And SQL Server uses this information to run these migration reports, which you can run, which tell you which tables will benefit the most by removing latch and lock contention, and which stored procedures will benefit the most because of the fact that they're used so often, and they use tables which suffer from lock and latch detection, contention. So if any of you are sitting here thinking, we have this application that has bottlenecks or that throttles on certain high throughput type scenarios, and it's not everybody, this is going to be a great fix for it. It's not going to be a silver bullet. You're going to have to do some work, but it is going to remove locks because it doesn't take locks, right? So there's definitely a place for this if you have that kind of challenge in your environment. So there are some ways to get there. There are some reports that you can run. You can use waits and queues, as always in SQL Server, to go and look yourself at where these waits are. What are my bottlenecks? What are my pain points in SQL Server? Perfmon, been there for a long time. Of course, you can go and use Perfmon. DMVs to to look for latches and locks, amongst other types of things. So none of this is really new. I'm sure you guys have been working with these tools now for a long time. But what you do have in Management Studio are these reports to help you identify those tables, which I will show you. We've still got about a quarter of an hour, so I'll show you that in just a moment. And these tools will help you, as I said, identify which tables you should migrate and which stored procedures you should migrate. You know, what's the lowest hanging fruit? Which are the ones I should go for first? That's what these reports are going to do for you. Yeah? All right, so let's have a quick look at this by way of our last demo. That's not the demo. That's a nice picture. All right, so let's have a look. So what we're going to do is we're going to run a workload. And what this workload is going to do is it's going to run for about 25 or 30 seconds, and it's doing a lot of on-disk activity and traditional stored procs. So it's just hammering my database, normal tables, not using in-memory OLTP, just doing disk-based lookups and inserts. But it's doing hundreds of thousands of inserts. It's using a tool called OStress, which we've had for a long time, which is a tool that you can use to do multi-threading or scaling tests. It's been around forever. So I recommend you use it. And we've got about, 20 seconds or so in terms of that. So the reason for doing that is so that I can show you something useful in this report. So what you would do, that's AdventureWorks 2016, you'd go off to the reports and you'll see this transaction performance analysis overview. So this is a report, this is where you'd start to look at your reports. If you're not running SQL 16, but you're running SQL 14, you can still get at these reports, but not unless you install MDW. All right, so I just want to remind you about that. You can't do what I'm doing unless you have the CTP. But for your SQL 14, yes, you can, but you need to go and get MDW. And then when you right-click on MDW and say reports, it will lead you to the same place that I'm showing you now. All right, but you won't have MDW, you won't have this management data warehouse unless you install and configure it. So now if I go and look at tables, I say, well, okay, I want to do this, but which table should I start? Where am I going to get the most benefit from my in-memory OLTP transition? So I've got here high gain going up on the up arrow here on my y-axis, and going across on the x-axis, I've got the amount of migration work. So I'm aiming for stuff up in the right-hand corner because that's got the least migration work for the highest gain. That's how this graph is working. So it's telling me, you know what, if you're going to do it, go start with this table, which isn't surprising because that's the table that little batch file I ran is running hot against. So what it's going to do for me, it's going to come back and it's going to say, well, start here because this is the table that's experiencing the most locks and the most latches. And if I turn this into an in-memory table, it will go to 0. That's a big deal, right? I can't just turn a switch and have that happen, although I'm closer to doing that in 16. I might need to do some work, but it's a big deal to do that. And this tells me where to start, all right? And I've got a similar capability for my stored procs. I've got a very kind of similar thing that I can do, and I can say, well, go and show me the stored procs, which is the stored proc I just showed you. Right, so I can say, well, this one's going to be high gain, so I'm going to go and look at that. I don't get as much useful information about the stored proc, but the reason it tells me to start here is that this is the stored proc that's been used the most, right? And it also tells me which tables that stored proc uses. So if I was going to do that, I'd have to go to each of those tables, and I'd have to convert those tables to be an in-memory table, which may or may not be easy depending on what my application looks like, but I would be able to do it. I might need to change some SQL. And once the underlying tables are in memory, then I'm going to come back and change this stored proc to be a natively compiled stored proc, which is going to generate some C code on the fly and load a DLL that's specifically targeted, and I do mean very hardwired at compile time, to process these 4 structures. And now that's just going to fly, right? But it's not free. But as I say, that there is a lot less work in SQL 16. So that's kind of where that's happening. What you can also do, you can go through these individual tables, like this one, for example, and I can say Memory Optimization Advisor. So I can go to the tables and say, okay, I've just figured out that I need to do these tables, so how am I going to do that? And then I start looking at the table and say, okay, what are the things that might be stopping me from taking this particular table and converting it into an in-memory table? And in this case, it's saying, hey, you know what? You've got a default constraint on the table. This product needs to catch up with the implementation because it's saying things like foreign keys somewhere. No foreign key relationships, right? So things like that. But I'd have to go and take out that default constraint before I could convert this table. So it's a little kind of process that you'd be following to do that, right? And the same for stored procedures. So if I go and look at a stored proc, how are we doing for time? If I go and look at a stored procedure, I'd see similar things, and I'd get advice about how to migrate that particular stored procedure. So insert sales order in mem, or on disk, sorry. This might be one that I'd have native compilation advisor. So tell me the things that I need to do to modify this stored proc to make it natively compiled. And it would say, well, 1 or more unsupported SQL statements in your stored proc. Well, I better go fix it. And in this particular case, what it says is I've got a begin transaction and an end transaction, begin and commit. I've got what's called an explicit transaction. Begin, do some stuff, and commit. You can't do that within memory. It's an atomic transaction. It's specified in the header. It determines commit rollback semantics as part of the syntax of the declaration of the proc. So it doesn't support this type of code. So I'd have to go fix it, right, on my test system. All right, so that's just a little and fast example of how you do that. And I did hear someone quietly saying test system, because I got good hearing. You might surprise you. Yeah, you need some test systems. Not having a test system isn't going to work well for you, regardless of SQL or anything else. All right, so just a little bit of a recap, just a kind of lightning fast list of the changes and some of the things that I've been talking about that take you from SQL 14 to SQL 16 in terms of this technology. And I really want to summarize by saying you can still do this in SQL 14, right? SQL 14 has been out now for quite a while. We do have a number of customers that have deployed SQL 14. A third of the people in the room is a bit smaller than I would have hoped, but it's not too bad. But it's certainly out there. It's mature. It's solid. We're not seeing lots and lots of support cases around SQL 14, and I'd encourage you to deploy it in production. I can think of no reason not to do that, other than vendor support, which is always the challenging elephant in the room. So you can do this on your SQL 14 systems. There's just more work, and you need to be aware of the constraints and the extra effort that's involved in order to do that. All right, I've got one more decent bit of swag here. Actually, I've got two. So I've got to think of some more questions on the fly, which is always tricky. So I mentioned in SQL 14 that you needed a specific product in order to generate these advisory reports. But hands up, what was the product called? MDW. And the very last one that we have. So these days there's a lot of talk about SQL Server. We've got lots of other types of data structures that are not relational. We've got cloud-based stuff. We've got NoSQL. We've got all kinds of things like that that's going on. What's the strictly correct product name for our Microsoft's PaaS, Platform as a Service, SQL Server database product? Ooh. Ooh. Azure database. You might want to. I might decapitate a few people. So just quickly, again, we've got about 5 minutes to go, and I do appreciate the time, everybody. I really appreciate that. So some other sessions that you might want to think about. One of them's already gone. We've already seen David's session this morning. This is the session you've just arrived at. There's one called BI in the Cloud. A gentleman I used to work with, Rob Hawthorne, he's talking about how you can do BI end-to-end through a cloud deployment. I think that would be interesting for folks if you're doing BI. Number 4 is a gentleman that used to be my manager. His name is David Downs. He used to own the Comedy Club in Queen Street. Fascinating guy, very, very interesting to talk to. And he's got a session, what's the difference between a developer and a lawyer? I just have a feeling that will be a lot of fun. So just think about it depending on what else is going on. And then a shameless plug for mine and David's 2 sessions on Friday. We're going to talk about this concept of Elastic SQL and what's that all about. And then the last session on Friday, normally everyone's gone home by then, but if you haven't, we're going to talk about all of the new things in SQL Server 16 and why you might find them interesting. So I'm going to be here this afternoon. I'll be at the hub on the desk, and I'll be around the place this afternoon if anybody wants to come and talk SQL because I really enjoy that. So I'll just take a couple of questions very quickly. Just before I take the questions, here's some resources for you as always. Everything's on Channel 9. And please do the evals because they are kind of important to us and I would appreciate it.
You mentioned that we have to take care of the files that are created for this technology.
Yes.
Are they considered as part of the files of the database that are in the properties of the database, and are they backed up and restored with the database?
So the question is for everybody, I mentioned that I have to take care of the files that are created by this Hackathon technology because we have these data files and these Delta files. And are they part of the database and do I have to back them up? The answer is yes, 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 and yes. They are all part of the database. They are backed up as part of the backup. You do need to take care of them. Think of them as being your MDF files. They're very much part of the database structure. One more question.
Are there specific DMVs related to in-memory?
There are specific DMVs related to in-memory. There's about 20 of them. All of them have the name HK_ in the name. Thank you very much, guys, and enjoy the rest of the week.